Hi, everyone. Once upon a time, there was that big monolith. It could be a big computer consisted of, I don't know, IBM System Z, AS400, VAX machine, and so on. As already mentioned, it was just one big computer with one big software with some sort of UI, if you can call it that way. And of course, large data stores, where in most cases were based on DB2. Later on, you had more siloed systems and operating system, where you could find some old versions of Linux and Unix operating systems, the old Windows operating systems, which were more of an application than an OS as of today. Of course, the classic MS-DOS and data stores. Later on the year, you would find a lot of different architectures and multi-tier type of system, more distributed systems in practice, where you could find more siloed type of systems from your ERP all the way to your client relation management systems and go for content management systems, and in general, data stores again, where the data was stored both on the server side, but also on client side. Speaking about client side, the client side was already independent in that period. And then the new era. Suddenly, all of the 2-tier, 3-tier, 4-tier, N-tier architectures started to show up. API is the king now. Relatively simple scale-out capabilities started to be more popular. Cloud, well, I would say that with IaaS and PaaS, they have started to emerge to the public cloud ecosystem. About SaaS, I have a different theory that it was already exist even before the public cloud was announced. But that's for another talk. And then data. When it comes to data, I would like to cover different type of dimensions and benchmarks about how it looks like in cloud, and later on I will touch upon the challenges, or the security challenges, so to say, and the potential solutions related to data security. So I'll start with structured data. Structured data could be in the form of a CSV file, a YAML file, a JSON file, a B-tree, and so on and so forth. When it comes to unstructured data, you would find things like unstructured text or unstructured audio file with its analog representation, but also its binary representation as well. You could find pictures in their analog representation. By the way, those two adorables are my kids, which I'm super proud of. And also their binary representation as well. So that was the structured versus unstructured data. When it comes to logical versus physical medium, on the logical side of things, you would find object-level data, which is managed by an application in most cases, and has custom metadata, which varies and arbitrary. Then you have the file-level type of logical medium, which is managed by the operating system itself, things like NTFS, extension, for, and so on. And it has fixed file system attributes. You also have the block level when it comes to storage devices in most cases, where it's also being managed by the operating system of that storage device, and it also has fixed system attributes as well. Now, when it comes to the physical medium, you have the non-volatile physical medium from hard drives, whether SSD or magnetic. You have the flash drives, USB key, mass storage devices or equivalent, and you have like optical mediums like DVD, which are less in use at the moment or in these times. And when we were speaking about the volatile type of memory, then you have things like RAM, random access memory, which are by all means volatile, but you also have processor registers, which also are even more volatile when it comes to the frequency of the data exchangeability. Then we have on-premise versus cloud, where on on-prem you would find, the central local disk of a given data center or an ecosystem. It could be also a central storage platform. It could be the local disk over the different bare metal services. While in cloud, the way that I put it is the data is somewhere over the rainbow because you don't really know where it resides. Now, there are multiple security challenges when it comes to cloud, but I would like to cover specific data security challenges when it comes to different cloud implementations. So I'll start with some direct challenges which related to public cloud. First one would be the fact that data can leak, the data leakage and prevention in cloud, which means how do you protect your data from being leaked from your internal environments within your public cloud to be exfiltrated outside of this particular environment? Then you also have the data segregation and protection, or in other words, how do you segregate your data in a by-design multi-tenancy ecosystem, also one of the biggest problems. Threat and vulnerability management, I think that's a clear challenge, which also relevant to on-prem, but when it comes to cloud, it's a bit more tricky because sometimes you are using specific systems or middlewares which you cannot control all of them and entails shared responsibility models, which sometimes doesn't adhere with your service level expectations. Identity and access management, here I must say that if you're using single public cloud, that problem or that challenge is in a better state as of today because of the evolvement of the different public cloud in the space of IAM and the practical granularity and implementations. But it might be a very tricky and challenging one when it comes to multiple public clouds. For instance, using AWS with Azure, with GCP, and then when you would like to govern them all, it is feasible, but more of a challenge in comparison if you were using a single cloud tenant. I'll skip the application security for one because I'm going to touch upon that from a different perspective later on. But the physical and personnel security, here it's pretty straightforward. Here, it's not your data center, meaning it's not your controls. And in some cases, it's also not your personnel. And the fact that it's not your personnel imposes a high risk in particular cases and in particular threat scenarios. When it comes to the indirect risks, here it's about different type of risk which are not directly to the cyberspace or to the cybersecurity misuse cases, but more about the processes and the people. For instance, if you need to have the ability to support business continuity and disaster recovery plans securely, that means that in particular scenarios, your organization might have state-of-the-art, highly mature security implementation for all of the different domains, from access control to infrastructure security, to application security, to data. But then think about a scenario which is, let's say, highly likely to happen for each and every organization. When you have a problem, when you have an incident, by the way, not at all cases it would be a security incident, but a incident that you need to act upon it. And in that incident, it might be that some implementations or some actions, required actions, entails with, I don't know, sharing sensitive data to specific third party, not in the standard way that the organization already facilitated. Now, the business is really vocal about that particular action that needs to be done in order to have, kind of the business more resilient as a result of this incident. But it might be that this implementation needs to happen fast. And as part of the need of that implementation to happen fast, it might influence the security level of that implementation. For instance, maybe that data needs to be shared in a different channels, not in a secure manner, not with key exchange, not with a secure password sharing and any other implementations for that. So sometimes that would require a senior leader to accept the risk of that particular implementation, and that, at the end of the day, is going to be a risk, or a data security risk in specific, which was only as a result of, excluding the security implementations and what can go wrong in the BCP and DRP specific plans. So that's the first indirect challenge. Second one is availability of services and data in the cloud. Think about your security implementations or data stores resides in one-stop shop. I don't want to name vendors, but it could be that you have your encryption mechanism, your sensitive data detection mechanism, your access control, your infrastructure security, your configuration benchmark, all of your security implementation ecosystem alongside the data repositories in one place or under one vendor. Is that secure? Can something go wrong with that? The answer is yes, and highly likely in comparison to the other way of distributing your different implementations in different vendors and ecosystems. The last one is about incident response arrangement. If you remember, on the direct physical and personal security, I mentioned the fact that this is not your data center, means not your controls, and also in many cases not your personnel. Think about the shared responsibility model. Think about an incident that happened which involves both the cloud, but also maybe potential either other public clouds or on-prem, other data centers. What can go wrong? Who is responsible? Who needs to contact whom? Did you set proper SLAs? Did you check that people are able, the relevant personnel from the different vendors are able to respond in a timely fashion, in the right expected quality, like you have with your personnel, and so on and so forth. So, again, when it comes to data solutions, I think here I would like to cover the different elements and benchmarks when it comes to the different consideration that I would advise you to take, not on all of the different solutions, because it would take me maybe a week to talk about all of the different benchmarks per domain. But I'm going to focus today not only on data security, but specifically on the subdomain of data protection type of solutions. And I'm going to start with the data truncation implementation. First of all, just to explain it, data truncation is about shortening an object or piece of datum to a way that it would be only partial, which means it's not going to disclose any sensitive element as a result of being exposed truncated. Now, the key pros with that approach is that you're getting full protection by all means. But it's full protection because you just cutted the piece of data that makes it sensitive. So that's why it makes it with full protection. And there is a big con as a result of that, which I'm going to touch upon in a moment. It's also relatively easy to implement. Truncating a piece of data is something pretty easy to implement if you know how to code and if you know how to use specific libraries to make it feasible. And also, not less important, it has negligible footprint when it comes to performance. And that's very important if you're thinking about really high-scale data stores or data processing elements, speaking in petabytes or hundreds of terabytes when it comes to daily routines. And that's a very important piece for that. Now, when we're talking about the cons part, here, as I've already mentioned, the fact that you get full protection, it's nice as a pro when relevant. But sometimes it also means that you cannot retrieve the full piece of data. It was cutted, truncated, so to say, from the original datum, which means you cannot get it back. And if you need it back, probably truncation is not going to be your optimal solution. The other con that we have is that it doesn't preserve uniqueness at all times, which means think about simple scenario. You have a credit card number and you haven't masked it, you truncated it. So it might be that the truncated part now not disclosing the full PAN, which means you are compliant and you're doing it securely and you're reducing the risks. But it might be that if you need to preserve uniqueness for specific business processes in the organization, and for companies dealing with credit cards, there are many use cases like that, then you can find yourself having the same piece of data, meaning that it's allegedly duplicated, but it's not, because originally it was different. And that's why not having the uniqueness part being preserved is a big con if you're using truncation. The next data protection implementation I would like to cover is data hashing. And here it's about mapping arbitrary size value to fixed size value. And just to be clear, I'm assuming for this particular implementation, proper hashing implementation, which meaning strong salt and strong hashing algorithm. Now here, the main pros to use that is that it's highly impossible to retrieve the original data from the hash value itself. By the way, I will divide my statement here into two parts. Mathematically, scientifically, it's impossible. But from practical standpoint, it might be that you hold a dictionary or a rainbow table in the more professional language, which means you have some sort of a dictionary with specific hashes to specific original text. And if someone will have the right way to put their hands on that rainbow table and they have enough computing power to run and query all of the above, they might be able to find a bypass, a workaround to retrieve from the data, the original data, from the hash value. Not mathematically, not scientifically, but as a bypass. The other advantage that it has is that it's highly injective. Hash preserve uniqueness almost at all times, and we're speaking about 99 point, many nines after the decimal point of being also impossible to be not injective. And that really helps when you have the scenario that you need to have injectiveness, you need to have the uniqueness of the data, but you don't want to ever disclose the original datum. And the next advantage would be low performance impact. Similarly to the truncation part, even though that takes a bit more computation power, it's still relatively cheap from performance perspectives. And that's very important when it comes to large-scale applications. The main con of that is that you cannot retrieve the clear text data from the hash value, and that's given because that's part of the attributes and the qualities of hashing. So, as I've already mentioned, it's a con if you need to retrieve the data eventually from the hashed value, but it's a big pro if it's unnecessary. I'll move now to tokenization. And in tokenization, the definition of that is turning a piece of data to a random unique string and use the dictionary to bind them all together. Here, the dictionary is not a bypass. The dictionary is a byproduct component of tokenization. Now, the main pro of tokenization is that tokenized data is completely pseudo-random, I would say. I cannot say completely random scientifically. It's meaningless if the tokenization application done right, and it doesn't provide even a small hint on the original data or the tokenization algorithm. Again, assuming proper tokenization. And that means that it's a big pro because here it's not about any encryption keys, which I'm going to mention in a moment, or any other type of implementations which gives you a structured output, which not in all cases that's the expected result. And I'm going to mention that in some of the other pros now. The other pros, it's about help to reduce regulatory scope. That one is not straightforward, and I would like to elaborate about it. So you can ask yourself, why tokenization help you to reduce the regulatory scope, but I don't know, hashing doesn't, or encryption doesn't. And the main idea for that is that with encryption, if you think about the idea of being able to retrieve the data, the cipher that you will find in the allegedly non-regulated scope, when it comes to things that you would be able to retrieve with a given key or another assistant, that would mean that even though it's protected and it's secure, it doesn't necessarily mean that it reduces the regulatory scope. For instance, with PCI DSS for cardholder data environment, or for GDPR when it comes to where you store or hold any privacy-related information, personal data in specific. So that's about that particular part. With tokenization, I'll just mention that if you have a tokenized data in the so-called out-of-scope environment, then all you have to do is to tell all of the relevant stakeholders how do you protect the dictionary, why the dictionary cannot be exposed or, let's say, leaked in a way that would put that ecosystem or that environment in scope for the relevant regulation. So that's for that particular pro. Now, another pro that it has is that token can be format preserving. Now, for those of you which are already expert in that field, you probably know that encryption can also be format preserving, but it's not the same, and for encryption you are much more limited, and I'm going to touch upon that, when it comes to in which way you would like to preserve format. Not at all cases you can design it like with tokenization platform, which giving you almost any way to preserve your format when you would like to implement a tokenization strategy for your data protection of your sensitive data. Main cons for tokenization. So you need to put extra measures to protect the token dictionary. As I've already mentioned, here the dictionary is everything. If the dictionary is insecure, all of the implementation of tokenization would make your sensitive data to be insecure almost similarly. And that puts that particular component in a very high risk, in a very high inherent risk, even without the controls that are going to be applied. Another con that we have is that it requires a lot of high maintenance, and there's a lot of performance impact as a result of most of the tokenization implementations. Because when you're based a system on dictionary type of implementation, that would be, I would say, more expensive from a performance perspective than a system which does things in a minimal computation implementation, like with encryption, truncation, and other type of data protection tactics. And then we have also the partial incompatibility, because with tokenization, this is not a standard way to protect your data like with encryption or like with hashing. You know, with hashing you can say, let's use standard protocols. With encryption you can do the same, and I'm going to touch upon that in the next slide. But when it comes to tokenization, most of the tokenization implementations are proprietary in a way that the implementation itself and connecting it to your systems, it's not going to be straightforward. And now I am arriving to the data encryption topic, which is one of my favorites because it also entails very large sub-components or sub-implementations, and it's it considers a very rich world, and I'm going to touch upon some of these items. First of all, let's start with the definition of encryption, because many people are getting a bit confused when they're being asked, what do you think is the definition of data encryption? So I think the essence is turning a piece of data to something which is a pseudo-random, I'm correcting myself or correcting the slide, pseudo-random unique string in a way that the only way to retrieve it would be with a key, some sort of key. And again, there's many definitions of what key can be. Now, with all of the dimensions that I can cover, there are like very, very large set of implementation tactics, from symmetric to asymmetric implementation, transparent versus payload, the mode of operation, the encryption algorithm, the architecture, which is super important and can be your weakest link if you're not implementing it right. But I'm not sure we're going to have enough time to cover all of them, so I'm going to cover some of these benchmarks. And I'm going to start with the symmetric versus asymmetric encryption. So first of all, just to explain what does it mean, symmetric in the sense of symmetric key versus asymmetric key implementation. And here it's about starting with the symmetric part. If I'm touching upon the main benefit of it, so it has very low performance impact. By the way, mainly due to the relatively small size of the encryption key when it comes to symmetric encryption. The main con of it is that you use the same key for both encrypting actions and decrypting actions, which means that that key is not only safe to provide it to anyone which needs to encrypt only. Now you also need to protect that same key, even though it needed for some entities only for encryption, you must protect it as much as it's the same key that has the same authorization or the same privileges to decrypt the data from cipher to original text. And that's a big con when it comes to specific implementation, when you need to distribute some of your encryption-only keys. Other cons would be that it imposes higher risk for the same reasons that I mentioned in the pro part, because the key size is shorter than in asymmetric keys, which I'm going to mention in a moment, which means it's relatively easier to break it. And even if you're using very strong keys, at least for today's times, don't forget we're in the era of quantum computing, and we really don't know what time is going to bring us and by when. So other I think I already covered the symmetric part. Moving to the asymmetric part, so here the main pro is that the encryption key is a public knowledge only, which means if you have a business scenario or technical scenario when you need to share your key for specific entities, even entities that you partially trust or even don't trust at all, but they are part of the data flow or the business process, that means that you can be calm with providing them only the public key, which they can only encrypt data that only you or other entities are privileged to decrypt it, but they would never ever be able to decrypt it with that particular key, or what it calls more commonly a public key in that setup. Other pro of asymmetric is that you don't need extra controls if you only need to encrypt, as already mentioned. If you need to provide only the public key, you can share it in an insecure medium, you can share it in any other ways, you can let that data or that particular key to be publicly accessible on the third-party premises without concerning that that key can also potentially decrypt the data in the previous scenario with symmetric keys. The con of asymmetric implementation is that it has very high performance impact because of the key size. Now, for those of you which might not aware of, the main implementation today for asymmetric key is mainly for key exchange processes. So all of you probably heard about SSL, TLS, and in general, secure channels which are based on TLS principles. In that principle, you're using asymmetric key only for the initial key exchange of a symmetric key that would serve that particular session to encrypt data in transit. Again, in a nutshell, it's a much more complex topic than that. But the main idea is that because it's high, it has high performance footprint, that's why it's been used only for the initial key exchange and not for the whole session, even though it's more secure by nature than a symmetric, shorter sized key. Now, other benchmark that I would like to cover is transparent versus payload. Here, first of all, maybe it's good to define what does it mean transparent and what does it mean payload. So I'll start with the transparent part. Transparent encryption, it's implementation which you're doing mainly underneath the layer you're trying to protect. So if you would like to encrypt data in all of your database, you would encrypt all of the DB itself, the DB management platform, the file of the DB, if you like. If you would like to encrypt all of your laptop disks, you would do it in a full disk encryption implementation. That would be considered as a transparent encryption. So the main pro of this type of encryption is that you have low performance impact because it uses different mechanisms with shorter keys and other implementations, which makes it with low performance footprint. It's relatively easy to implement in most cases because in the majority of cases, it's out of the box by different vendors, either operating systems vendors like Microsoft or Apple, but it might be also for RDBMS platforms, for instance, MySQL, MS SQL, or others. And it's relatively easy to implement as a result of having a standard type of implementation by the vendor. It has no modification needed to done on the client side because it's supposed to be a transparent implementation. That's why it's called a transparent encryption. And it's very effective when you need a low-level protection. Think about the scenario of your laptop being stolen and has a lot of sensitive data. For the scenario of a thief putting their hands on your laptop, I think that's a good implementation. For other scenarios, when someone has an access to your operating system, it's a different story, which I'm going to cover on the cons part. So moving to the cons part, it's ineffective for most of the attack scenarios, as already mentioned. If you have a full disk encryption, as an example, or full DB encryption, but you have your DBA or your users having access through a proxy, or through a listener, or through any sort of means which are not underneath that layer, that means that it's transparent, which means you would not see the data encrypted. You would see it in clear at most cases. Depends on how you've implemented it. And it's a big con if you don't understand what you're doing in that particular implementation. Now, it's also not applicable for all platforms. I already mentioned it might work with MySQL, with MS SQL, with Windows, with macOS, but you cannot implement it with each and every platform. So you need to be aware of that. And it's ineffective for OS level if you don't have a trusted platform model. Think about full disk encryption, where you store the key also on your disk. So it's a bit of the chicken and the egg, because you cannot encrypt it with the same key that you're encrypting it. You need a key encryption key that would be available upon decryption. Now, that can be done in a very low risk if you have trusted platform model, a TPM, which is a mini HSM equivalent, which can be chipped in each and every platform. If you don't have it, it's not effective, hence it's a con. When it comes to payload encryption, just to explain here, indifferent than transparent, we're speaking about encrypting the piece of data itself and not the whole ecosystem of it. And the main benefit of it is that it's effective for most attack scenarios. If you implement it right, that means that you can have a scenario where the data is encrypted at all times, and it might be only decrypted while in use, either in the client specifically, when it's really must being decrypted and displayed to the user, or in a backend type of processes where you have the data being decrypted only when it needs to be processed. So that's why it's highly effective. But the main cons of that is that it has mid-high performance impact. Sometimes it's mid, sometimes it's high. It really depends on the level of implementation, because in most cases, it's a proprietary implementation which requires specific ways how you're protecting that particular data and in which granularity level. It doesn't have to be a field or a value like in JSON. It could be like a bulk type of, or a table. It really depends how you've implemented it. Other con that we have, it requires modification on the client side in most scenarios, assuming that you implemented or applied that solution in a way that you would like it to be encrypted end-to-end until the very last mile on the client side. Not all organizations or system designers would like to implement it in that level, but you need to be aware of that because it's highly secure if you're doing it like that, but it requires a lot of modification, which sometimes can be a pain for the people which in charge of kind of making the clients to be adhere to the new applications. And the last con would be that for most of the third-party solutions, it's not supported by product. You need a library for that. You need to develop something that would literally take piece of data or bulk of data, the payload itself, not the layer underneath, and would effectively apply proper encryption and proper decryption on the relevant parties and the relevant parts where it's mostly needed. So, as I've already mentioned, we don't have enough time to cover all of the different sub-components or sub-benchmarks under data encryption or other domains, but I wanted mainly to give you a taste and more of a look and feel on topics that even though today we have many new cutting-edge innovative solutions in that field with full homomorphic encryption and no decryption at all and using fragmented keys and so many innovative things, I think that the basics are still very important for everyone to be aligned upon, because that's what would help people and would help organizations to apply proper data protection, from the essential parts. So a couple of conclusions and takeaways for this particular talk. So from data security perspective, on-prem is not public cloud. I know that you knew that, but I wanted to emphasize that particular part mainly when it comes to the different misuse cases, the different attack scenarios, and the different solutions you would like to apply in a given either public cloud from one kind to another public cloud and to other on-prem implementations which are different. The second one is that there are different motivations for data protections. Some organizations just want to tick the mark to say, we're compliant with this, we're compliant with that, and in some cases, they will do the bare minimum, which means it's not going to be practically a risk reduction implementation, but more of satisfying the regulatory requirements or satisfying the auditors that will sign off the particular attestation for that organization. But there are also other motivations which I believe are super important, because if you have the right security maturity level, that means that you can also increase your reputation level with your customers, with your partners. I think with customers it's more likely with B2B type of organizations where your business customers expecting you to show higher maturity levels when it comes to security, especially when you're processing their sensitive data. And the other one would be that you have different constraints to consider while applying different data security solutions for different ecosystems, different business cases, and different type of applications. And the very last takeaway that I would like you to take is that please, please, please don't just take a ticking the mark type of solution and just, say that you've done and applied the data protection. I've already mentioned the transparent encryption earlier. I think that's a good example of things that if you're doing it for things like laptops or other type of scenarios, be very clear with yourself about why this type of solution with that type of implementation helps in addressing this particular threat or misuse case. Otherwise, you're just ticking marks and you're not doing it right, at least in the way that I see things. Thank you very much.
Which data security solution do you think is the best in case that I need to retrieve the data and to be cost effective?
So, of course, there are a lot of unknowns for me to answer that question more structuredly, but I would mention mainly data encryption. I'm taking the cost-effective part, and I already mentioned that tokenization might not be the most cost-effective one. Using or applying proper encryption for your solution with the right key management platforms, using HSMs, other security models, or other implementations, followed by the right key architecture, which means you have local master key. Underneath, you have zone keys for different entities, and underneath, you have data keys, which are being rotated frequently and being audited and being monitored. Using that and applying it right, I think without having more knowledge on the ecosystem you're probably asking about, that would be probably the most close answer I can provide to you.
Thank you.
Related to the data.
Yeah.
Could we apply or should we get into labeling the data somehow so we can maybe improve some of the cost, or we should treat the data the same?
So that's a great question, and I have long dedicated talk only about data visibility, classification, labeling, and tagging only on that topic. So to provide you a concise response to your question, yes, you're highly likely in the following sequence to classify, to discover your data, okay, to classify your data, then to label your data, either internally in a designated system or in the relevant data store, and to tag the data for other users when someone else will consume the data. Because today we're in the era of data production, data consumption, Kafka architectures, these type of things. So to repeat my response concisely, you are highly requested or expected to discover your data, There are many mechanisms to do that, on-prem, cloud, unstructured, structure. There are many solutions for that today. Discover your data, classify your data with minimum false positives and maximum precision rates. Then labeling the data, and afterwards, if and where possible, tagging the data. Because then it would strongly help you to have better data governance, but also better data security as a result of that, because you know where your sensitive data resides, how it's been protected, how it's been in use, who has access to it, and how you can effectively control the security level of that data.